And I think last time we were looking at some problem on the slides, right? On the PowerPoint slides, is that right?
That sounds right.
Let
We
me
just
see. I
lost.
usually write down what we are doing. Yeah, the last thing that we did was example 5.15 A through C, I think.
Okay. I'm sorry, was that from the slides or from the handout?
I believe it was from the slides. That was just.
Okay.
I usually write an outline so that when I go over the video again, I know where I need to go if I want to look something up specific.
Yeah, yeah. Okay. So let me see what we have here. I think we talked about all of this, types of probabilities. I think we were on this table here, weren't we? This is what we were working on.
I think that we were right past that at the Venn diagram. Yeah.
The Venn diagram, right. Okay. Now, was this clear, the Venn diagram, how it worked?
Yes.
Yeah, yeah. So this is another way of looking at a table like this. We can call this table a 2x2 table. Well, not a 2x2 table, but basically it's a table with two variables that are that we're examining together. And N represents, of course, one of the variables, and D represents the other one. And we can always, and I think there was a mistake in this slide, right? Because the N, not N and not D, should be the 2563 here, obviously, right? Because it's 2563 is intersecting not N and not D. So this is a mistake here. This arrow should be pointing down here. The 404, of course, is representing what? It's representing D and not N, right? D and not N. That's the 404. So we'll just go over it again. The 31,575, we can say is N, but not D, right? 14,131 is N and D, which is this number. 404 is not N and D. And the 2563 is this, what they're saying here. It's not N, not D. So all four numbers are shown here, right? All four of them, these four. And of course, if we add 14,131 and the 31,575, we get N, North America. And that's this whole circle here. We add those two numbers. If we add now, if we add these two numbers for dry, 14,131 and the 404, we get the 14,535, right? We get that number there. So the question is, where did we get this number, the 2967? Well, that's the sum of these two numbers, right? It's the sum of this number, 2563 and 404. The sum of these two numbers is these two here. Right, that's where the 2967 comes in. All right, so I think we have it all, right? Don't we have it all? I believe. Any questions about this?
Nope.
Now, also, if you wanted to say N or D would be what's inside the two circles. And of course, we eliminate the duplicate of 14,131. So we simply add these three numbers. That will give us what's inside N or D, right? So it's N plus D minus what's in the middle, or the sum of these three numbers. That gives you N or D. Okay, so it's really this number plus this number plus this number would be N or D. And of course, this here would be not N or D, right? That's what this number would be, not N or D. Again, I can go into more detail about this. Oh, actually, here we go. There's a special rule in this type of logic that says not N or not D is equal to N and D, not the whole thing. In other words, you change or to and then you put not around the parentheses. This is a special rule. You could also say not N and not D is equal to N or D in parentheses not. So you just switch the and or. You see how that works? It's like a distributive property for the not. When you distribute the not across, you change the and to an or to an and. And maybe I'll write this out. It's I think it's called the De Moivre's theorems or equations. He was a French mathematician who came up with this. He proved it. But this is a convenient way of looking at it. For example, not or not D. We know that N and D would be what? What's in the middle here, right? So not. So if we say not that, it would be everything else other than what's in the middle. It would be N only. All right, which is this one here is N, not D. This would be D, not N. And this would be not D and not N. Okay. So that would be the answer for this. Any questions about that? Oops, sorry about that. We do spend a long time on this problem here. So the probability of N, I think we already did something like this with the previous one, would be 45,706 divided by the grand total. The probability of not D and N. Ooh, which one is that? Well, not D is this column, and N would be this number, 31,575 divided by the grand total. All right. What's the probability of not D or N? That's a little trickier, right? Not D or N. Now, the way to do this problem, the simplest way of doing it, is list what not D is. Not D would be these two, right? These two, the sum of these two. N is what? These two. What's being double counted when we look at these two and these two? The 31,575 is being double counted. You simply just add these three numbers, right? And you should get the answer, I believe. Although that's not what they have here. Let's see. Not D is these two. So this is not D. And N is this number here. So it would be the sum of these two numbers minus the 31,575. Okay? The sum of these two numbers minus 31,575 would give the numerator. Okay? So I believe, I don't know if they're doing this right. Let me see. Add these two, not D or N. You add these two and subtract what's common, which would be this. Doing it right? Really 2563 plus. Now, I don't think they're doing this problem right. I don't think this is correct. I don't think this is correct. Wouldn't it make sense the way I'm doing it? Not D is this column, right?
Yeah.
So it'll be the 34,138, or n, which would be this row. And then we subtract out the duplicate. The duplicate between this column and this row is the 31,575. So not quite sure. Are they doing that here? Yeah, they're doing it right here, right? All right. So if you add these two and subtract, that's the correct solution. Yeah. So I would pay attention to A here. A looks right. All right. Do you understand how I did it? I simply added the marginal totals. This is the or means add, right? So add means you simply add the probabilities. Now the denominator is going to be the same for both of these, right? 48,673. We're just looking at the numerators. The numerator of this is 34,138. The numerator of n is 45,706. This row, and we subtract whatever's common between them, which is the 31,575. That's the reasoning behind that. So I like the solution A the best. I think it gives you the correct answer. The rest of these, I'm not sure if, I mean, I think it gives the right answer, but I'm not sure of the reasoning that they use for those. I think A is the best reasoning. All right, I'm not going to spend a whole lot of time on this one. Do you get an idea of how to do it with a table? Yeah. Okay. Now, when they say simple probability, they're talking about the marginal probabilities. Okay. These the margins. These are the margins. These two numbers and these two numbers divided by the grand total. They're calling simple probabilities. Okay. But so, for example, probability of n. That's a marginal total. That's this total divided by the grand total. All right. So marginal and simple. I like marginal better because it means it's in the margins. I always like that term better when explaining this and using the word simple. There's also it also can be called unconditional because there's no conditions on it, right? There's no other information. Probability of n is the probability of n without any other events. So it's simply the marginal total for n divided by the grand total. If I say probability of D, it would be D is this column, 14,535 divided by 48,673. All right, get the idea? So those are the marginal probabilities. The joint probabilities would involve these four numbers here. These would be the joint probabilities. Okay? Whenever you have the word and, that's joint. But simply one of these four numbers divided by 48,673. Of course, we could also have conditional probabilities here too, right? That is, what's the probability that we selected somebody who is in South America? What's the probability that the well would be, I guess it's well, right? The well would be dry. Well, if they're in South America, then the group now is 29,667. That's our denominator now, right? Because if we're selecting from that group, that is wells in South America, then we're selecting from this group. We're ignoring North America. We want to know how many were dry. It would simply be 404 divided by 2967. If we selected a well at random and the well was not dry, what's the probability that it was in North America? Well, if we select a well that is not dry, then we're ignoring the dry ones and we're left with 34,138. That's our denominator. And out of those, the ones that were in North America were 31,575. So it's 31,575 divided by 34,138. Okay. So those are the types of questions I could ask, right? in probability questions when you see a table like this. The table makes it a little bit easier because you can actually see it. And also these kind of strange ones here where you have not D or not N, and then you have and or, you can simply use the product rule. Okay, the product rule. Or now with and, you don't even need to use the product rule here. You don't need to use a multiplication rule here, because the word and is telling you what? It's giving you one of these four numbers. So this one is easy to do when you have a table. One of these four numbers is going to be your numerator. When you have an or, then you have to use the addition rule, right? And you're going to add the marginal probabilities and subtract a joint probability. Okay. So you're adding, like in this case here, you're adding this number, which is marginal. You're adding this number, which is a marginal total. And then you're subtracting this joint number here. All right. So you're using the law of addition, probability law of addition when you're doing this one. All right. Everybody good with that? Okay. Now they say simple and or marginal. I'm going to use the word marginal. Marginal and joint probability share a denominator, and that's because you're selecting from the whole sample or population, whatever you're selecting from. If it's a survey, it's from the entire sample. The only time the denominator will change is if we're selecting from one of those marginal totals. All right, we're selecting from one of those marginal totals. In other words, we're selecting from one of these totals as opposed to the whole sample, right? So when we do conditional, we say, oh, I'm selecting somebody from South America. Well, I'm selecting from this group, not from the grand total anymore. I'm selecting from a well that's not dry. I'm selecting from this number, okay? So the denominator will only change if it's conditional probability. I'm talking about the denominator. I mean, they make this point about the denominator sharing the same denominator. Well, the denominator only changes if we have a conditional probability that we're talking about. Otherwise, the denominator stays the same. Because it's the whole group, right? The whole sample. And that's what they're saying in this last little statement here. Watch what happens with conditional probabilities. Right? And that's exactly what I was just talking about, right? So conditional probabilities with a table. You don't need any special formulas for this because you simply look at the letter that comes after the vertical bar. And that tells you which marginal total you're going to use. If it's D, you're going to use 14,535 as your denominator. If you're using N, you're going to use 45,706 as your denominator. If you were going to, if this here was not D, you would use 34,138 as your denominator. If after the bar it says not N, we're going to use 2967 as your denominator. So the first letter before the bar is what? This is a this is the probability of N and not D. Well, that has to do with what? It has to do with a joint probability here. A joint probability. And actually, when you see the formula for conditional probability, the numerator is the joint probability of these two events. And your denominator is the marginal probability of the second letter here. That's your denominator. So probability of N bar at D, which is the probability of N, given you have information about D, is going to be this joint probability of N and D divided by the marginal total for D. If it's D, probability of D bar N, it's still going to be the numerator is still going to be the joint probability of D and N. It's still going to be this number, but in this case, we're looking at the event for N, which is North America. So that's our denominator. Probability of not D given N. Well, not D is this number. This is not D and N. And then this is the total, 45,706, because it says N here. What's the probability of N not given not D? Not D is what? This number. That's our denominator. And the joint of N and not D is 31,575. So it's these two numbers that are taking the ratio of. All right. And this is the point I was making, right? Conditional probabilities are the only ones where the denominators are different than the total sample. It's one of these four marginal totals. It's going to be your denominator. Any questions about that? Susan, any questions about that? And then here's the formula I was just referring to. Conditional probability of A given that event B has occurred. When they say event B has occurred, meaning that we're still finding the probability of A, but now we know something about this other event called B. So it's the joint probability of A and B divided by B. If we were going to reverse this and say, what's the probability of B given A, the numerator is the same, but the denominator becomes probability of A. Okay? And once again, if we're dealing with a table, and both the numerator and the denominator have the same denominators, right? The numerator is a fraction, denominator is a fraction. They have the same denominator, so we can just simply cancel them. That's why it works out the way it does. Okay, does that make sense? That's why we can say it's simply the count for N and D divided by the count for D. All right. Now, earlier we talked about events that were mutually exclusive. Mutually exclusive is used in the addition rule for probability. The addition rule for probability says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, right? That's the addition rule. And then if the events A and B are mutually exclusive, then they have nothing in common. And therefore, the probability of A and B is 0. So for the addition rule, when two events are mutually exclusive, the sum of the two events is equal to probability of A plus the probability of B. Now, let's go back a minute to previous page, this page here. We take this equation and multiply both sides by the probability of B, we get a multiplication equation. We multiply both sides by the probability of B, we get probability of A and B is equal to probability of A given B times the probability of B. Okay. And now, here's another definition, which has to do with multiplication, because that's what we just did, right? The conditional probability equation becomes a multiplication rule when we multiply the denominator by both sides of the equation. If events are independent of one another, what does that mean? That means the marginal probability of A does not change when the event B shows up. That is, If A and B are independent, the probability of A given B is the probability of A. It hasn't changed. In other words, the information that B provides does not alter the probability of A. So that's called, they're being independent of one another. You see the difference between that and mutually exclusive. Mutually exclusive means they can't occur at the same time, A and B. Okay? If A and B are independent, they can, of course, occur, they will occur at the same time, right? If they didn't occur at the same time, they'd be mutually exclusive. But independent means that, yes, they're occurring at the same time, but the presence of the other event doesn't change the probability of the first event. So we would say two things in this case here. The probability of A given B is equal to the probability of A if they're independent. We would also say, this is important, and I don't say it here, just to be complete, that if it's the probability of B given A, that's going to be equal to the probability of B. The probability of B doesn't change if A arrives. So you both have to be true. If A and B are independent, it doesn't matter which one you're looking at, which probability you're looking at, the presence of the other is not going to change that probability. So there's two equations you would say here. If A and B are independent, you would say this one, and then you would say also the probability of B bar A is equal to the probability of B. So both of them have to be true. You can't have one and not and say the other one's true. That doesn't make any sense. If this is not true, then we say the two events are dependent on one another. That is, the presence of the other event changes the probability of the first event. Okay? So let's go back again to this equation. Once again, if we multiply both sides by the probability of B, notice it's a multiplication rule. Probability of A and B is equal to the product of a conditional probability times what? The probability of the condition, right? However, if they're independent, this probability becomes the probability of A. So the probability of A and B becomes the probability of A times the probability of B if they're independent. In other words, we take this probability and we replace this one with this one in this equation when we multiply both sides by the probability of B. Right? I'll show you that on the on my handout. My handout's clearer than this. Well, I did the handout. Okay. The same thing, like I said, is true for the probability of B. Now, we go back. The probability of B given A, in other words, we reverse these two, put B first and A second. The numerator stays the same, but the denominator becomes the probability of A. So if we multiply both sides, we'll get the probability of B given A times the probability of A. Once again, if A and B are independent, the probability of B given A becomes the probability of B, and then it becomes the probability of B times the probability of A is equal to probability of A and B. In other words, it looks exactly like this. All right, again, I'll go back to the handout to make it clear to you. I know what I'm talking about, but maybe you don't know what I'm talking about. But I'll get to that. Well, again, if they're not independent, they are dependent, which means the occurrence of one event does change the probability of the other event. In other words, this becomes, if they're dependent, these two are not equal to each other. Okay? And then we have to go back to this equation here. So maybe what I'll do is I'll stop right here for a second. Go to the handout, which is here. Okay, here we go. Now, and it's basically on the second page here, or third page, whatever, page 4, 10 pages. Page 4. I have both the addition rule here. You see that in general, this is the general addition rule. Now I'm using, instead of or and I'm using union, which means or, and this upside down, which means intersect. This upside down U means intersect. That's and. So this is the general addition rule. And notice if A and B are mutually exclusive, this becomes 0, right? They don't intersect. If you drew a Venn diagram, those two sets would not intersect at all. There wouldn't be anything in common between the two. Okay, that's an easier one to understand, I think, mutually exclusive. Now for the multiplication rule, we know that if they're independent, we simply multiply their probabilities. The probability of A and B, we simply multiply their probabilities. In general, we have two possible equations. When I say possible, because it depends on the problem that we're looking at, or the multiplication rule. We say the probability of A and B is either one of two things. It's either the probability of A given B times the probability of B, or if the conditional probability is reversed, it's the probability of B given A times the probability of A. Okay? Depends on the context of the problem, which one of these we're looking at. And it says where, and here are the conditional probabilities. I hope you can see this, right? Conditional probability, the numerator stays the same in both equations, but it's what's after the bar here tells you what the marginal probability is in the denominator. It's B in this case, and it's A in this case here. And these two equations simply come from multiplying the denominator, both sides of each equation. When we multiply by probability B, we get this equation, and we multiply both sides by the probability of A, we get this equation. Okay, you see it? Okay. Not as clear in the book or the slides, but I think that's why I wrote it out this way, so you can see it. All right, so, and it says here, probability of A, probability of B are the marginal probabilities, and the book calls them simple probabilities, which I think is not clear what they mean. And probability of A and B is a joint probability. All right, now, Stephen, you talked about Bayes' theorem. Bayes' theorem, of course, is used a lot in the medical field. All right, so it's something that, and I wish I had, let me see if I have my other book here. Might not have it with me. All right, okay, maybe, oh, here it is. This is the other course I teach at Rowan, and let me just see something here just for a second. There is a section in this other book that deals with relationships between in one of these tables here. Let's see if I can find a term that I want to use here. Just give me a second here. Find it. I know it's in here, but I think a lot of students who are taking statistics for the first time find some of this kind of hard to understand. So, see if they have it here. No, I guess I thought it was in here, but maybe it isn't. Many times with Bayes' theorem, you're interested and you're given information, a conditional probability that it's not what you're looking for, and you want to find the other one. In other words, maybe you're given the probability of A given B, and you're not interested in that one. You're interested in the reverse, the probability of B given A. So what Bayes' theorem does, it takes advantage of the fact that, hold on one second here. Takes advantage of these two equations, right? These two equations right here. The fact that the probability of A and B is equal to either one of these is what Bayes' theorem is using. So in the problem, whatever problem we're looking at, we will be given the probability, the probability of A given B. All right. We're also going to be given some of these marginal probabilities. They'll be given in the problem. Now, if you're trying to find the probability of B given A, we know the numerator is going to be the same as the numerator if it was the probability of A given B, right? It's the same probability of A and B, the joint probability. So that doesn't change. Now here is the conditional probability formula for this. But we're going to convert this numerator to the other conditional probability, the one that's reverse of this one, the one that we were given, which is the probability of A given B times the probability of B. That's the multiplication rule. Now the denominator says the probability of A. Now what is the probability of A? And this is where maybe you got a little confused when you saw it. The probability of A, if there's only two events, A and B, either A occurs or B occurs, okay? Then the probability of A must be equal to the probability of A and B, or the probability of A and not B. Does that make sense?
Yeah.
Yeah, it has to be the sum of those two. It's either one or the other. Either A is with B or A is with not B. Okay? And that's what these two terms are. This is the probability of A and B, which is the joint probability of A given B times the probability of B. This is the probability of A and not B, which is the probability of A given not B times the probability that it's of not B. And all of this information here is given in the problem. It's either given or you can derive it. All right? It's either given or you can derive it. All these things you can plug in. Once you plug it all in, you get this answer. You get this answer. Right? So let me give you an example of this. All right. I have a good example. There's two examples in here, but one of them is kind of convoluted. Like this one here. This is a convoluted one. I'm not going to get into that one. This is the one. Or is it? No. This is the one. This is on page 156, number 49. And let me just read it. This is a clear example, one that can easily 156 and number 49. I'll read it. It says there machine A. So you have three machines actually. Machine A, machine B, and machine C, and it produces something. All right, and they're all producing the same thing. And then through some maybe some studies that you've done, you've discovered that machine A has about 3% of whatever they're producing as defective. Machine B has 5% being defective, and machine C, 10% of whatever output it's creating is defective. So that's what it means when it says machine A produces 3% defectives. It means out of all the products that it's producing, 3% are bad, and that should be thrown out. I'm not saying it will be thrown out, but should be thrown out. Now, total output from these machines. Well, 60% of the total output comes from machine A. 30% of the total output comes from machine B, and 10% of the total output comes from machine C. One item is selected at random from a day's production. The first question is, what is the prior probability that the item came from machine C? What is a prior probability? Prior probability means a marginal probability. It means before we got information about defectives or anything like that, it's just the probability of the item that we selected is from machine C. So we know that machine C produces 10% of the output over the long run. So if we select one at random, the probability it's from C is 0.10, 10%. That's the answer for part A. So you didn't need Bayes' rule for that. All right. Now look what before I answer anything else, look what I wrote down here. I wrote down what the problem gave me, and then I wrote, actually, this is all what the problem gave me. Probability of A, notice you selected an item at a unit at random, the probability that it's from machine A is 0.6, from machine B it's 0.3, and from machine C it's 0.10. Those are marginal probabilities, right? There's no other information for those percentages here. Now, machine A produces 3% defective. Notice how I wrote this here. What does it mean? It means that if D is the event that one of these units that's being produced is defective, right? It's a defective part or defective whatever. When I say 3%, that machine A produces 3% defectives, that means if I chose an item from machine A, I know it's from machine A, the probability that it's defective is 0.03. Isn't that true? Isn't that what it means? If I know that, if I select a part from random from machine A, just from machine A, the probability that it's defective is 0.03. That's exactly what it means. When I say so it doesn't say machine A, it doesn't say here the conditional probability or anything. It doesn't use those terms. It just says machine A produces 3% defectives. But remember, this shop here has 3 machines. We're looking at the grand total. It would be the sum of those 3 machines, right? What's being produced in 3 machines. But when we say machine A, we are now restricting ourselves to the output from machine A. So that's why I'm writing these as conditional probabilities. The probability that a part is defective, given that it's from machine A, is 3%. The probability that a part is defective, given that we know it's from machine B, is 5%. The probability that the part comes from machine C is defective is 10%. Now, the second question here says, if inspection finds the item to be defective, that's the condition. All right, we now know it's defective. Therefore, and then it says, what is the probability, the revised probability the item came from machine C? So the probability of C, given that it's defective, we know it's defective. Isn't this the reverse of what's this one here? It's the reverse of this one, right?
Mm-hmm.
We're given this, we're being asked to find this. This is where Bayes' theorem comes in. That's the only reason to use Bayes' theorem, is if we're given one conditional probability for 2 events, and we're being asked for the reverse conditional probability. Otherwise, it's not necessary. You don't need it. So, what do we need in this problem here? Well, we need to convert. First of all, we need to convert what we want into what we're given. Now, the numerator for this is going to be the probability of C and D. What we're given, this is where I was talking about before, of what multiplication rule do we use? Well, we're going to use what's given to us. This is what's given to us, this one right here, with reference to machine C. You know, if we were being asked about B or A, we would use those, but we're not. We're being asked about machine C. So we're going to be using this. This is what conditional probability that we're using. So the numerator is the probability of C and D, and we want to use this formula using this one, the probability of D given C, because that's what's given, times the probability of C. That replaces the numerator of this conditional probability. The denominator becomes what? And I'm looking at it here, and hold on one second. Let me see if I did this correctly. I think I did, but all right. Now, yeah, I did it correctly. The original conditional probability says this is the probability of C and D divided by the probability of D. The probability of D, all right, involves actually three pieces here. It's the probability of D given C times the probability of C. In other words, this is the probability of D and C. This is the probability of D and A, and this is the probability of D and B. So we're going to, again, this is the probability of D and C, which is the probability of D given C, because we're given that, times the probability of C, which we have, plus the probability of D given A, which is this one, times the probability of A, which is this, and the probability of D given B, which is this one, times the probability of B. Again, we're using what? We're using the multiplication rule. But we have three of them here because we have three machines. Okay? Notice the numerator is just one of these three. It has to be. It's always that way. One of the sums that you see in the denominator in Bayes' theorem is always going to be the one that's in the numerator. Which means the following. If I want to know what's the probability of A given D, right, in this problem here, then I'm going to be using this one in the numerator, and the denominator is still the same thing. The denominator is going to stay the same no matter which conditional probability we're asking for here. The probability of C given D, the probability of B given D, or the probability of A given D. Okay? Whichever one we're being asked for, we're going to choose one of these three to be in the numerator. The denominator is going to be the same. And then if you just plug in all these numbers, you get 0.233. And what was the original probability of C? 0.10. So probability of C, given that we know it's defective, right? The probability, what's the probability of C if we know it's defective, has actually increased from 10% up to 23.3%. So it's changed. That's the revised probability, given that we know it's that the item that we chose is defective. Okay. Anybody have any ideas why would it go up instead of going down? It could go down, right? I mean, it's revised, it could go up or down. The reason has to do with a couple things here. It has to do with the fact that this number here is the largest of these three. You see it? 10%. So the numerator is going to be what? Remember, the denominator is going to be the same. The numerator is actually the largest number, 0.10. Now, you might say, well, wait a minute, is the probability of C is smaller than the other two? All right. You have to kind of look at this probably in a lot of detail. see why it went up. There's probably a couple different things that are moving up or down. The important thing is it did get revised upward. It did get revised upward. And it would be interesting to actually, as an exercise, find the probability of A given D and see if its probability went up or down. Because A is 0.6. What do you think? Do you think it's going to go down, most likely?
For A? Yes.
Yeah, it'll go down, right? It probably balances itself out, right? One of them goes up, or maybe two goes up, and one goes down, whatever. They're not all going to go up, and they're not all going to go down. There's going to be a mix of those, all right? But that is this kind of helpful a little bit, this particular problem, in terms of understanding how Bayes' theorem works?
I think so.
Okay. All right. I think you have to look at it and maybe do more of these, right? So as an exercise, if you want, do this problem as if it was machine A instead of machine C, and come up with your answer and see if the probability is revised up or down, and do the same thing for B. Okay. Now you don't have to do it, but I would strongly suggest that you do it, because I might give you something like this on your test number 2. All right. By the way, I'm working. I have. Oh, I didn't mention this, but I have completed the 2 quizzes. I did post them to start from tonight, but I haven't had a chance to make sure that everything looks okay for the 2 quizzes. So I'm going to change the start date tomorrow to noon, and it's due next Tuesday at 8:30 before the class by 8:30. So you have, I originally made them 20 minutes, but I think I'm going to revise it up to 25 minutes just to give you a little extra time. All right, because you're not used to seeing a quiz like this. Now, I would suggest, just as a little sidebar, I would strongly suggest, now quiz number 1 is on chapters 1 and 2. I did use chapter 1, all right? So chapters 1 and 2 have a lot of, especially chapter 1 has a lot of definitions and things like that. So I would strongly suggest that you read them again before you take the quiz. All right, I will give you 5 more minutes, 25 minutes, but if you don't, you still may not finish it. There's only 5 questions. There's only, basically there are 5 statements with multiple fill in the blanks, either 2 or 4 fill in the blanks for the 5. So it's either, 14, 16, or 18 blanks that you have to fill in. And so I'm going to change also the time to 25 minutes just to make sure you have enough time. But again, if you try to take the quiz without reviewing before, you may run out of time before, because you're searching for everything. And before you know it, you've only completed like 60% of it. So that's what I recommend. And the second quiz was on chapters 3 and 4. There might be it may be a couple of them that deal with very brief calculations. And I mean brief meaning brief, not much to do. All right. All right. But I will get the start time. I'm going to revise it to tomorrow at noon, so I'm going to make sure everything's good to go. All right. Any questions about the Bayes problem here? They have a second one here, which you can look at if you like. But this one is a lot harder than that one. And I had to think about how to do this with Bayes. It's not easy to do it with Bayes. You have to set everything up correctly, and it has 2 parts, 5.45 and 5.46, and the Bayes part comes in at 5.46. But I'm showing you my solution, but I'm telling you that I would not test you on a problem like this. This is an example of Bayes' theorem where it's kind of hard to understand. So It took me a little while to figure out how to set it up. But I'm showing it to you anyway, so you have no an example where it's kind of hard. Now, let's actually look at some of these problems. Let me make sure I covered everything. Yeah, I did cover everything because I think in the handout, if you've looked at it, I went over the ideas, basic ideas of probability. And these are just the basic definitions and things like that. And then the classical relative frequency and subjective approach of probability. Notice that when we use a table, we're using the relative frequency approach, right? Because the survey is basically the number of people in the survey would be the number of trials and the experiments being repeated. So if you're asking a question, you're asking the question over and over again to all those people. That would be the relative frequency approach. The odds, again, I've showed you a little bit here. I might ask, on a test, I might ask you one little question on it, but don't worry so much about it. I'm not going to make it an extensive thing. I show you the rules for addition with the mutually exclusive idea, multiplication with the independent idea, and I showed you Bayes' theorem. Let's look at some of these examples. And actually, wait a minute, I think time is almost up. Would you want to go 5 more minutes? Would 5 minutes be okay, or would you want to stop now?
I can go 5 more.
5 more minutes? Okay, let's go 5 more minutes. I don't want to keep you too late. Otherwise, Han, your family is going to start attacking me at a distance. So. All right. Some of these questions are pretty simple. On page 139, 5.4. And it says here, electric meters on private homes in a community register the cumulative consumption of kilowatt hours with a 5-digit reading, right? If a home in the community were randomly selected, it's possible that the right-hand digit, that's the 5th digit, I'm assuming they're would be a 7. Now, it can be any number from 0 to 9, right? Using the concept of classical probability, what is the probability that the digit is a 7? Okay. We're only looking at the 1 digit, right? The other digits we're assuming are fixed, right?
Mm-hmm.
We're only looking at the last digit. There's 10 digits, has to be 1 out of 10. So it looks like a complicated problem, but you're really just looking at that 1 digit. Okay. So that, to me, that was a trick. That was not a hard question. It just looks hard. 5.5 says, how might an observer employ the law of large numbers to verify the classical probability that you identify? Well, the law of large numbers says you need to repeat this experiment many, many times, not just one home, but maybe thousands of homes, right? And then you do a frequency approach, relative frequency approach, and the more meters that you read, the closer the relative frequency probability will be to this 1 divided by 10. There should be one. It should be closer and closer to this 1 out of 10 classical answer. Okay. Any questions? 5.6 says if a die is rolled 1 time, classical probability would indicate the probability of a 2 would be 1 out of 6, right? Because there's 6 possible sides. If the die is rolled 60 times and comes up 2 only 9 times, does this suggest that the die is loaded? Well, you might, 9 divided by 60, which is what the relative frequency approach gives you, is between these 2 fractions, 1 divided by 7 and 1 divided by 6. 1 divided by 6 is the classical answer. So you would say, I would say basically, no, it doesn't mean it's loaded. It just means maybe we haven't done enough trials. It would have to be much, much different. So different from one divided by 6 that you could think it can't be by randomness that occurred, all right? That you start thinking maybe it's loaded. But if it's different, and it seems reasonably different, there's no reason to think it's loaded, just maybe you just didn't do enough trials. And the answer is no. It's probably, there's no reason to say it's loaded, because the answer, 9 divided by 60, is not so different from 1/6 that you would think there's some issue with, right? It seems like it would be a normal variation. Number 7, the number of deaths per 1,000. Well, actually, let's look at number 7. A newspaper article reported that Massachusetts, this is the last one we'll do, unless I think maybe 5-8. All right, but we'll do the next 2 and then we're done. So 5-7 says a newspaper article reported that Massachusetts had become the 2nd state after Montana to prohibit sex to be used as a factor in determining insurance premiums. In other words, they should use the word gender in this case, right? Gender. Now, considering the information in table 5.1, 5.1, table 5.1 is on page 137. It's basically looks like some sort of actuarial table for an insurance company where they're looking at the number of deaths per 1,000 for life insurance. Okay. Now, considering the information in this table, and since Massachusetts is saying they're not going to consider, they're not going to have, basically what the Massachusetts decided is they're going to charge one premium for both men and women or other. Okay, it's unisex premium. They're not going to divide it up. So, based on what you see in the table, what do you expect the unisex premium to be relative to what it would have been if we were able to charge a premium for men and females? Would the men's premium going up or down, or would the women's premium go up or down with the unisex premium? So if you look at the table, it's universally true, no matter what the age of the person, that the mortality rate per 1,000 for men is higher than for women. You look at every single one of those ages, it's true. And in life insurance, if mortality rate's higher, assuming everything else is the same, all the other factors, the premium's going to be higher. Makes sense, right? They're going to charge more. That would be in a state where they are able to charge separate premiums. So if you picture them combining the 2 groups together, right? The women's group would draw the men's group mortality down, and the men's mortality would draw the women's mortality group up if they mix them together, right? The total mortality. So you can picture with unisex premiums that the premiums would be lower for men and higher for women than if they were separate premiums. And that's what they're asking here. All right. Does that make sense?
Mm-hmm.
Yeah. 5.8, the last question. It says it's been reported that about 35% of U.S. adults attend a sports event during the previous year. What are the odds that a randomly selected U.S. adult attended a sports event during the year? Well, this is the odds of in favor of attending the sporting events as opposed to not attending one. So the numerator is going to be the probability of attending, and the denominator is going to be the probability of not attending. And I hate to express it as a fraction because it really isn't a fraction, but basically the answer is going to be 7 to 13. So the odds of attending a sporting event is 7 to 13. because 0.35 divided by 0.65 is 7 divided by 13. So you would answer, and you always answer it this way, 7 to 13. Okay. And it would make, does it make sort of make sense? The odds would be 7 to 13.
Yeah.
Now, if we were given these odds and we were being asked what's the probability of attending a sporting event, then we would add these two numbers together. That would be our denominator, and the first number would be our numerator. It would be 7 divided by 20, and 7 divided by 20 is 0.35. That's how you double check your answer, by the way. All right. So I think that wraps it up for tonight. Now, once again, the quizzes. I'll have them ready for you, even though they're ready now. Don't start them, please, because I do have to change the start dates till tomorrow at noon. They'll be due Tuesday at 8:30, by 8:30 before our meeting. I am working on the exam number 1, which is for chapters 1 through 4, which is a mix of, I would say right now, it's a mix of questions like little scenarios where the answer has to do with a concept, all right, such as observational studies versus experimental studies, or a population versus a sample, all right, where I'm not going to just ask you what's a population, what's a definite. No, I'm not going to do that. I'll give you a little scenario, and I'm going to say, all right, what's the population, what's the sample, or in chapter 4, I might give you a little scenario and say, what type of sampling is this? I'll describe the type of sampling, and then I'll say, what type of sampling is this? I might repeat it a couple times and see if you can understand the difference between the sampling methods. Then what I'm also doing is in Minitab, I'm creating charts and graphs, and I'm copying them in there, and then I will ask questions regarding those too. So each of these scenarios might have 2 or 3 questions connected with them. The whole idea is I'm going to have it's multiple choice. I'll probably about 22 of these, 5 points each, 110 points, where there's extra credit being thrown in. And I'll limit the time that you can take it. Typically, it'll be a class time. So classes, if we were in a regular class, it'd be 1 hour and 15 minutes. I'd limit it to 75 minutes for 22 multiple choice questions. All right. That will be due next Thursday before class, but I haven't finished it yet, and I will send you an email. I want you to work on those quizzes first, but I will probably have that test done by probably by Sunday, early Sunday. So you'll have Sunday, Monday, Tuesday, Wednesday, part of Thursday to have it done. All right. Now I know you guys work during the week. You don't have a whole lot of time during the week, so you may want to spend time. That's why I'd like to have it done early Sunday, so that if you don't really have much time during the week, you can work on it on Sunday. But it's not the type of test where you can just work on it and stop. Once you start it, you have 75 minutes to complete it. All right. So make sure that you feel like you're ready to go with it. All right. And it covers the material and in the first 4 chapters. Make sure you understand all of the calculations that we went over. There's a couple things we didn't go over, right? Like line charts and things like that. Things that we skipped, I'm not testing on, but everything else is possible. All the ones that I mentioned, even the bar charts and the pie charts and things like that. Even the quizzes could mention those too. But again, you have the book available. It's all there. If you review and then have the book, you don't have to memorize things because everything's there. You just have to know where everything is. Okay. All right. Now, you may decide to wait to take the test until after the next meeting, right? Tuesday's meeting. You may say, I'm not really sure. Let me ask a couple questions about what's on it. You can always send me an email, but you may also want to wait till Tuesday if you feel like you'd rather have a chance to ask me a question about it, right? But I'm not going to tell you what's on the test. I will tell you what could be on the test. That way. All right. Any questions about that? So just remember that I'm giving you that extra 10 extra credit points on the test. So when you take it and you feel like I didn't do as well as I wanted to, just remember you have that extra 10 points there. So what I tend to do, because Canvas is kind of funny about the way it calculates your grade, it calculates it as a percentage. So if you do have extra credit points on your test, just for purposes of Canvas, I have to multiply your grade by 1.1 so that the overall grade comes out correctly. When I multiply by 1.1, that resulting number is not your grade. It's the number that you actually got in terms of points. But I have to make that adjustment to make sure it works in Canvas. So I have to say that ahead of time, and you probably asked me about it again, but that's okay. But it will work. Math works perfectly. So but you'll see. Anyway, each of the quizzes are worth 20 points each. All right. Yeah, all of them. So if I end up with 6 quizzes, we'll end up with 100 possible 120 points. The quizzes will not be extra credit. There's no extra credit there. And any homework or what I call projects, there's no extra credit there. It's only in the tests and also the final exam. If I have a final exam, there'll be extra credit built into that one too. All right. Any questions? Are we good? Okay. Okay. All right. So have a good weekend. And again, you can start the quizzes afternoon tomorrow. And I will try to work on it a little bit later tonight. I do have something else I have to do now, but I will definitely make sure the quizzes are ready to go by noon tomorrow. Okay. Have a good weekend. And I'll stop sharing here, I guess. And see you later. All right.
All right, bye, Professor.